How do microscopic defects form in additive manufacturing? Imagine building a complex object layer by layer, like stacking thin sheets of material. Now picture tiny flaws sneaking into the process, invisible to the naked but capable of causing big problems later. That's what microscopic defects are in additive manufacturing. They form during the process when energy sources like lasers or electron beams interact with raw powder materials. These powders are spread in thin layers, and then the energy melts or fuses them together. If this energy isn't just right, tiny issues can happen. One common way these defects form is when the energy input is too low. When there isn't enough heat, the powder particles don't fully melt. This creates what we call lack of fusion defects. Think of it like trying to glue two pieces of paper together but not applying enough glue. The bond isn't strong and weak spots can develop. These weak spots can crack under stress or load over time. On the other hand, if the energy input is too high, it can cause vaporization of the material. This creates gas pockets or pores inside the part, known as keyhole defects. These tiny cavities are like bubbles trapped inside a cake, and they weaken the structure. Porosity is another issue caused by these tiny gas pockets. These pores are microscopic voids that act like stress concentrators. They make the part less able to handle forces, which can lead to early failure. Porosity can also cause leaks in parts that need to hold fluids or gases, especially in aerospace or medical applications. Sometimes, unmelted or partially melted powder particles get trapped inside complex shapes or internal channels. These trapped particles can block flow paths or create weak points, especially in heat exchangers or turbine blades. Rapid cooling and thermal gradients during the process also play a role. When the material cools quickly, residual stresses build up and microcracks can form. These tiny cracks can grow over time, further weakening the part. Process instability, like spattering of molten material during laser interaction, can introduce unpredictable flaws. Variations in laser power, scan speed, or layer thickness can all influence defect formation. To prevent these issues, manufacturers use advanced monitoring techniques like X-ray computed tomography to detect microscopic flaws early. Understanding how these tiny defects form helps explain why some additively manufactured parts fail sooner than expected. They are often the starting points for cracks and fractures. By studying these defects, engineers can improve process parameters, optimize material choices, and develop better quality control methods. This way, we can make additive manufacturing more reliable and ready for critical applications in the future.